Want to talk about floating gate, floating gate structures, particularly applied to digital analog converters or DACs. And I want to start this with a very important point, that to actually get the linearity you want for a DAC or an ADC, it turns out, everything is at the question of matching. Matching sets everything. In one way or another, set your limits one way or the other. And so this is the great problem, because matching usually means devices have to get bigger. If they get bigger, we have more capacitance. We have more capacitance. We have other issues that come along with all of this. So the issue then is asking an interesting question. How do we get around this? It'd be wonderful if we could just simply, at the root of the problem, be able to program out any of these issues. And the cool part is when you start talking about floating gate devices, so often abbreviated just FG, it allows you to do the programming, but it's very specific because the primary issue in mismatch on most transistors, 0th order, is threshold voltage mismatch. If you're in subthreshold, it's far and away the issue. If you're above threshold, it's clearly the primary issue. There's a little bit on other geometry things, but since most high performance circuits are done near threshold or just slightly above threshold where possible, you're going to be facing this problem no matter what. So here's the thing. If I can program changes in threshold voltage in a capacitive network in the same way that the mismatch was created by charge, I can directly counter this. And there's been multiple examples of how this happens and how we approach this, even in terms of things that are over temperature. And so the way to start to think about it for DACs is that often what you're trying to do is create a whole bunch of current sources or create a bunch of voltage sources. So in this case, we talk about creating a whole set of current sources now that are just single transistors and have a floating gate in them, maybe something like we would see here. Now I do need to think a little bit about where the actual biasing of these are a little bit to understand some of the temperature dependence, but there's a whole conversations and literature around that at this stage. There's also a whole conversation around voltage sources, which actually don't really have a temperature dependence, if you typically have that floating gate and you're using like some sort of amplifier to drive it. So you could imagine starting with a whole bunch of floating gate sources. There's a classic work on EPOTs. There's classic other elements of having floating gate devices with amplifiers. The classic thing that typically works is to have a floating gate where there's a capacitor feedback around an amplifier to work with. That typically works best. But there's lots of ways to go, so I wouldn't want to stifle anyone's creativity. But what's amazing is you look at, say, a floating gate-based current DAC and current topology, meaning I'm trading current sources, and then I'm going to switch those and put those into a load. And what you find very quickly, even if I have plenty of other loads capacitance, but maybe not too much, is I start to realize, well, wait a minute, each of these transistors are the same size. Now I could scale them, and there may be some reasons I would do some initial scaling. Lots of interesting design choices there. But let's start with the view that they're all the same size. And so normally when I add an extra bit, I have to like double the amount of area of the transistors for the current sources. Here I just add one, and I just program it. Now obviously it depends on the programmability of it, but when we've actually been able to show 12, 14, and higher level of precision and programming, you're probably fine for most things you're building. And then it's just a matter of switching things accordingly as you needed to, and then use the current. Maybe you put it through a load to make something to go through there. Maybe use the currents directly. Again, depends on the architecture you're building. A similar structure shows up with the charge DAC kind of approach, where normally you would have expected all of these capacitors to be scaled, right? 1 capacitance, 2, 4, 8, and so on. Well, here they're all the same, because what I really am doing is I'm using the floating gate voltages to be programmed to a point to be all of the different voltages I'm looking for, and those get switched onto the one terminal of the capacitor. And this is really just meant to be a capacitive summation. And again, I still have the same maybe classical reset type of structure. And in fact, I can even argue if there's even slight mismatch of these capacitors, I could slightly tweak where the voltages are tweaking to. And so this is really pretty incredible what's possible with these devices. But to realize that we go from a sort of something that scales, as an exponential thing in the number of bits to something that's linear in the number of bits drastically changes things. And everything is about the fact that matching can be directly handled. And when matching is no longer an issue, lots of things get quite interesting in analog design.